Yes.
Okay, so we're going to have a go at deriving the equation for a mass oscillating on a spring. Maybe we'll set one up too and have a look at what that looks like.
Hey, you got it perfect.
Like oscillating.
Whoa, no chance.
Okay, so shall we
Yeah, it's pretty distracting though with all those like hanging things right behind it.
quite hard to focus on?
Yeah.
It probably still might come off, so it's not like...
Yeah, but let's lift it up, because where's the limit of like where it's going to come off? Like, what do we need for this to be simple harmonic motion?
It needs to start at
constant velocity.
No?
Constant period.
No? Yeah, but what do we need? Oh, what's the rule for simple harmonic motion?
The acceleration.
So the displacement and the acceleration have to be in opposite directions and have to be proportional.
Yeah.
So what's going to be the problem as I lift this up? What's happening? What's happening to the size of the acceleration? Downwards.
Increasing.
Increasing, and what's the limit? When does it stop increasing?
In the spring.
Where you
It's all
just...
the way coiled up.
Weightlessness.
When it goes.
There.
Oh, like that. Well, how much is that maximum acceleration? How much if I just dropped it now?
Probably
how much is
for
the
gravity.
acceleration? And so if I dropped it now, how much is the maximum acceleration? Nothing's changed, that's just hooked onto the spring. And so that's like the limit of simple harmonic motion. If we made that like any higher, if we do it, yeah, it might, if we're good, right?
Ooh.
Oh no, enough energy got wasted that it didn't. But that's like the limit to simple harmonic motion. So that's why doing it vertically is really, it's got a limitation. And so often they'll do you a problem where like there's someone on a trampoline and they're kind of bouncing up and down. And that's simple harmonic motion if their feet are still on the mat of the trampoline. But why isn't it simple harmonic motion once they start bouncing up in the air?
Do they accelerate themselves with the trampoline?
Did I teach it?
What's to do with acceleration? What's wrong with acceleration? It's the same, it's 9.8. It doesn't get bigger and bigger the higher they go. It's 9.8 no matter what, hey? So that's not proportional. So it's not simple harmonic motion if you start leaving the surface of the trampoline. But if you're just bouncing up and down and you're staying in contact, then that is simple harmonic motion. So that is simple harmonic motion now. That's like the stretchier the spring, the faster the frequency, the higher the frequency, the shorter the period. And what happens if we make the mass bigger? What happens to the period?
Slower.
It's a longer period, like a lower frequency motion. And what can you tell me about energy, like as this thing oscillates up and down?
Turning gravitational potential energy into...
Okay, so at the top, what sort of energy have we got there?
gravitational
Gravitational
potential.
energy. And then at that point, elastic potential. And then what about in the middle?
Kinetic.
Kinetic. And so over the course of like one period, we've got gravitational potential, kinetic, elastic potential, kinetic, gravitational potential. So it's going like potential, kinetic, potential, kinetic, potential. All in one period. That's all those energy transitions are happening. The thing that you should be trying to hold on to, like we're going to make an equation that's on your formula sheet, trying to capture the process that we're going through though, because if you follow the same process, you'll manage to crack, you'll crack that question, you'll know how to derive the equation. So, period of a mass on a spring, we're talking about, I've drawn it horizontally because it gets way more complicated if we've got gravity acting. If we just have it horizontally and the spring oscillates backwards and forwards, then when the spring is loose, that means that's equilibrium position. If we displace the mass this way, the spring pushes it that way. If we pull the mass that way, the spring tugs it back the other way. So we're just, kind of horizontally oscillating on a frictionless imaginary surface. So just remember about springs. We've got Hooke's law, F equals minus ky, where the y is the extension of the spring. Last year it was F equals minus Kx, but I've just written Y because we're using Y for displacement, so it's going to make it look nicer. And already we can see that this is kind of meeting the criteria for simple harmonic motion, because we've got a force that's in the opposite direction to displacement, but depends on the size of displacement. So already we're like, this looks like it's an SHM thing that could happen here. Using F equals ma, so A is F upon m, we can rewrite the acceleration as minus ky over m. And just remember that for simple harmonic motion, it's always A is minus omega squared y. So we've got this equation, like our fundamental equation from simple harmonic motion, and we've nudged the spring one until it's got the same form. That's the key thing that you've got to do to make this work. Now we look at that equation, A equals minus something y. Look at this one, A equals minus something y. We're like, those two somethings have to be the same thing. So we rewrite it as omega squared is k upon m. Omega, we remember, is 2 pi over t. We're trying to get the period, right? 2 pi over t. And so we're going to put that in. 2 pi over t squared must be k upon m. Square root. So 2 pi over t must be k over m square root.
Swap around the T and the...
Yeah, the old flipperoo both sides.
The old flipperoo.
And then you just times 2 pi over and you get the second equation. I should have used it.
Next step,
times
Times 2t.
get the 2 pi on the top. And so that one, that's on your formula sheet. And once again, we've got that same we've got that same unexpected discovery that the period of a mass bouncing on a spring doesn't depend on the size of those oscillations. Like it's going to be a big oscillation or a small oscillation. That doesn't factor into the period. The period only depends on the mass that's oscillating. Bigger mass takes longer. We expect that it's bulkier, it's harder to accelerate, it's going to take longer. Or gruntier spring, it's on the bottom. What does that do?
the bigger the grunt, the less the time.
Yeah, the bigger the grunt, the less the time period. And so by using a spring that's really hard to stretch, like we can kind of think about it in our minds, being like, oh yeah, if it's really hard to stretch, it's going to ping back really quickly and oscillate with a short period. Or a spring that's really easy to stretch is going to loll around a lot more slowly. Right? So we've got an equation that kind of makes sense in our minds. Yeah. Label it up. What's the K, mate? What do we call that thing?
Spring constant.
Yeah, nice. And spring constant's telling us the what?
How strong is spring?
How strong? What do you mean by strong?
How many inches?
How stretchy is maybe a better word for thinking about it, for understanding it. Like if it's a little k, that means it's really easy to stretch. Well, a little force is required to make an extension, whereas a big number for k means a bigger force. It's how many newtons you need to extend the spring by a metre, like change the length of the spring by a metre.